Hello everyone. Today we will solve a problem from SuMON fortnight. This problem is based on combinatorics and permutations, but also it involves some number theory into it. The idea is that you are given a set from 1 to n and you consider its permutations, and the condition of the permutation is that for every k less than n, where k is a natural number less than n, you must have the first k numbers leaving distinct reminders modulo k. For example, if k equals 3, then the first three numbers should leave the reminders 0, 1 and 2 in some order. That is, no two are congruent or leave the same reminder when divided by the number k. So we will solve this using methods in combinatorics. But you may take a moment to think about this problem and let's get started together. Here is the question we will be working on today. The set 1 to n is considered along with its permutations such that for each k less than n, the first k elements. For any permutation, we consider the first k elements for every k less than n, and all of these numbers should leave distinct reminders modulo k. That means all the reminders should be present in some order. The reason is because you have exactly k reminders modulo k, and the numbers under consideration is k in number, and thus you need to have all possible reminders starting from 0 to k minus 1. With this in mind, we need to figure out the number of such permutations. Now take a moment and think about the strategy or idea with which you can tackle this problem, and let's get started in few moments. Okay, now we will define a variable which we are going to actually find. That is, let Tn denote the number of permutations, number of valid permutations of 1 to n. Here the word valid means the number of permutations that satisfy the condition for each k less than n, the first k elements leave distinct remainder modulo k. Now we are going to include some recurrence that governs this variable. That is, we are mathematically modeling the property given in the question. How do we do that? Well, we represent recurrence basically means we represent the nth term of the sequence followed by Tn in terms of its predecessors, or as a function of its predecessors. That is, Tn in terms of Tn minus 1, Tn minus 2 and so on. It may or may not include some constant. Alright, so if you think about the n permutations, you have the first blank, second blank, third blank, fourth blank, and this is the n minus 2th blank, n minus 1th blank, and the last will be the nth blank. We will split this into two cases. Case 1 is that blank n contains the number n. Contains the number n. So under this assumption, we are going to express the valid permutations, the number of valid permutations in terms of Tn minus 1, Tn minus 2 and so on. So if it contains n, the last blank, then the remaining blanks which occurs before the last blank will have the numbers 1, 2 till n minus 1 in some order. But what is the number of such sequences containing 1 to n minus 1 without any gaps. This is basically Tn minus 1, right, by definition. So we are actually looking out for Tn minus 1 ways in this case, because we are only dealing with the numbers 1 to n minus 1, that too consecutively. There are no gaps and n is not involved in this system. So we are good to assume the rearrangement is only from 1 to n minus 1 consecutively. Alright, so this case will have Tn minus 1 permutations. Let's move on to case 2. Case 2 is, of course, blank n does not contain the number n. Alright, if blank n do not contain the number n, what could be the possible number in the last blank? First, let's contemplate about that. Assume that we have n minus 2 blanks represented together as the big red line segment. And then you have the last 2 blanks, that is the n minus 1th blank and the nth blank. Notice the condition given in the question. It should be valid for all k less than n. Suppose you consider k equals n minus 1. This means all these numbers leave distinct reminders modulo n minus 1. But we now have the case that n occurs in this list. Modulo n minus 1, n will be congruent to 1, or in other words, n leaves remainder 1 when divided by n minus 1. So that means 1 should not occur in this highlighted blank region, because n also leaves the remainder 1 and 1 also leaves the remainder 1 when divided by n minus 1. So we will push 1 to the last blank. Only then it could be a valid configuration. So now let's rethink about this. What are the numbers that we try to fill up here? We are interested in filling up 2, 3, 4 till n in the first n minus 1 blanks and 1 in the last blank. Now again we are going to represent this in terms of the preceding terms Tn minus 1, Tn minus 2 and so on. You could see that these numbers have the same relation for the numbers 1 to n minus 1. That is, number of ways to form a valid permutation with 1 to n minus 1 in the first n minus 1 blanks is the same as the number of valid permutation that can be formed using 2 to n in the first n minus 1 blanks. How could I establish such a relation? So, you see, after filling up the numbers from 2 to n in the first n minus 1 blanks, decrease every number by 1. If every number drops by 1, clearly it contains only the numbers from 1 to n minus 1. But how come that not affect the solution? We should be sure that it should not negatively impact the condition given in the question, right? So if you decrease 1 throughout, the first n minus 1 blanks, you are essentially keeping the modular value the same. How? Suppose consider the first k values. Suppose I consider the first k terms in the permutation. Let's say its sum is s. Or let's consider the remainders to be R1, R2 till Rk, modulo k. We know that these k terms leave the remainder 0, 1, 2 till k minus 1. because all of them are distinct modulo k for it to be valid permutation. Now, you are decreasing 1 throughout the k terms. Let's see what it impacts these reminders. 0 minus 1 is minus 1, which is equivalent to the remainder k minus 1. 1 minus 1 is 0. 2 minus 1 is 1. And so on till k minus 1. Minus 1 will be k minus 2. So you could see the reminders are 0 to k minus 1 in a different order now. There is a cyclic shift, I would say, by one number. But other than that, our condition is still satisfied. So valid permutation still remains as a valid permutation. And indeed, you can take back from 1 to n minus 1 to 2 to n by adding a 1 to the first n minus 1 terms. So this is called as a bijective relation or a bijection between the actual sequence to some desired sequence which can be counted easily. Why can this be counted easily? Because we know that this value is same as Tn minus 1. Because Tn minus 1 also have n minus 1, the first n minus 1 permutation in n minus 1 consecutive blanks, which is essentially the case we have here. Thus, totally Tn will amount to Tn minus 1 plus Tn minus 1 ways, which is 2Tn minus 1. This is the recurrence relation that governs the variable under consideration. Alright, we are done with the recurrence. But without initial condition, your recurrence cannot conclude anything about the actual value. Without spark, there will be no forest fire. So this is analogous to that. So we need that spark to find the actual values using the recurrence. What are the initial conditions? Consider n equals 1. That is, you have just the, or let's consider n equal to 2. That is, you have 2 blanks and the only possible permutations are 1, 2 and 2, 1. The condition is that this number should leave a distinct remainder, and of course modulo 1, that is true, and these two numbers should leave distinct reminders modulo 2, which is also true. Coming to this leaves a remainder of 0 modulo 1, and considering modulo 2, this leaves a remainder of 0 and this leaves a remainder of 1, which are again distinct. Hence both of these permutations are valid, so we conclude that T2 is 2. Now we will use this to build our recurrence. We see that T3 is 2 times T2 according to our recurrence. So recurrence is this first equation, and that is 2 squared. Similarly, T4 is 2 T3, that is 2 times of 2 square, which is 2 cube. Now you can observe a pattern here, and using that you may conclude that Tn is 2 power n minus 1. So this will be our final answer. That is, out of the n factorial permutations, we know that there are n factorial permutations. But out of that, you have only 2 power n minus 1 permutations that satisfy our given condition. That is, for each k less than n, the first k terms leave distinct remainder when divided by k. So recurrence is one method that always comes to my mind whenever I feel stuck or whenever I don't find a particular direction to tackle the problem. I hope this will also keep you informed about this method. So let's continue more discussions on strategies in several of our fortnight problems. Meet you in the next video. Until then, happy learning mathematics. Bye.